That's correct. I figured I could use this to send the message to the people who are not actually coming, but only watching it online. Yeah. Okay, yeah. So what is in terms of scheduling? So you might have noticed I posted the new project there, project number 4 on Canvas. Did you see that already? It's there. So you just need to look at it. And it's about what we talked about before, about the transform coding that leverages orthogonal transformations and this least squares business. So do some example very similar actually to the next ones, which I will talk about in like a couple minutes. So that's project 4. It will be due on Friday as usual. And the next week is the midterm week when I'm gone. I'm going to Japan, but there will be the TAs who will take care of the exam. So on Monday and Wednesday next week, there will be the midterm test. It will be the test in class, just like here, except that you will like sit and you will get like a piece of paper and solve some linear algebra problems, similar to what we are doing here. I might do some sort of review session, something like that, on Friday or maybe even on Thursday. What do you normally do? You might know better. Like some sort of like what type of things are in the midterm, or
yeah, like knowing what sorts of questions.
Right.
Practice problems, maybe.
Practice problems.
We could like do the problems on our own and maybe go over them in class.
What do you mean? What problems do you on your own?
Like if there were example problems or something, and then you can post them on Canvas, and we could like
That's
do
a
them on
good
our own
idea.
and
That means I'll actually have to do it, but I guess I will.
or maybe if there's any problems in the textbook.
Right. I mean, of course they are, right? I just yeah. That's a good point. Yeah, so we can do that, and then discuss it either on the recitation on Thursday or even in the class on Friday. So then you want to get all set. Then you can like review it again over the weekend if you want, and Monday and Wednesday will be the midterm problems. And yeah, it's not gonna be a big deal. I mean, if you follow the material in class, you should have a very easy time doing those best questions. Yeah, so that's for the coming week. And then on Friday, my plan is that the other TA would go over the solutions for the midterm, so to explain you how it was supposed to be solved, in case you were wondering. Okay, sounds good. Any other ideas, questions? The review think was a good idea. I'll have to do something about that. All right. So let's finish today the least squares business. Try to align this nicely. So this is what I ended with the last time, right? Remember? So maybe let me review first the basics of the mathematics. This was an example. So least squares is really a useful thing to have under your belt, because lots of SQR, lots of real world problems lead to that. And actually we can see it in this example. So let me actually stick with this just a little bit longer. So this example was about fitting a line to a set of points, right? Here I had in this case, 5 points in 2D, and my question was to find in some sort of best fitting line, right? So in what sense was this exactly best fitting? In the sense that if I compute for every point, if I compute the distance from the line in the vertical direction, so if I take this distance and call this D4, and this distance D5, then I want the square of the sum of these distances minimized. That was the sense in which I considered this line to be the best fit line, right? But obviously, if I wanted a perfect solution, if I wanted all these, so this is if my line is given by parameters m and c, then this is just an equation of a line, right? For arbitrary x, I get some y, right? And here we can see why least squares is so useful, right? Because the perfect solution, getting perfect equalities, that would have to mean that my input points are exactly on the line, right? Only in that case I can perfectly solve the system of equations, right? The problem is that there is more equations than unknowns. It's this rectangular system of this sort of format. If I have some interesting number of points, right? But presumably if you have just 2 points, then you don't bother with things like this. So I assume I have a bunch of points here. And if I have a bunch of points, it's pretty unlikely that it would be lying exactly on one line, right? Even if you give it just like a tiny bit of numerical noise, you know that the numbers in the computer are never exact, right? So if one of these points was like 1/3, forget it, right? It's not going to be represented exactly, right? Which means you cannot exactly solve the system of equations, and you would not find a solution. Even if the points look almost perfectly on a line, solving the equations would just tell you no solution, sorry. So that's why least squares is such a powerful thing, because it lets you find the solution even if things are not completely perfect. And they can be even quite weird, right? I mean, least squares will find you a solution no matter what. It will find you a solution even if these points go completely crazy. At any rate, there is always some best fit line, right? And that's what least squares will find you. If the points are reasonable, if they are close to a line, that they will find you a reasonable linear approximation. If the points are totally crazy, if it's like essentially noise, they'll also find you some line, but the line might not be that interesting, right? So let me recap the mathematics of least squares, because it's very important mathematics. So this is what we discussed the last time. But if I should just summarize it quickly, and that's probably all you really will want to remember. So the point is that I have a matrix m by n on the input, with m being greater than n. And I have a system ax equals b, which very often does not have a solution, right? Because my m is greater than n, right? I could include this case greater or equal than n. In the special case that m is exactly n, it is not overdetermined, the system. But most usually you have some measurements from a real world thing, and you usually have like a lot of measurements, right? So this m can be like really big. And the n is the number of parameters of your model. In this case of the least squares fit of a line, it was the number of parameters of a line, right? So just 2 scalars. Okay, so this has in general no solution. Now it can have a solution in special cases, right? On the example of the line, if you are so lucky that the points actually are exactly on a line, right? If everything was perfect, like for example like this, right? And I actually hit integers, so I don't have any rounding errors and so on, then sure, I have a solution, perfect solution. But it's really unlikely, right? It's like probability 0 sort of event. Probability 0 means it actually can happen, but it's infinitely improbable. So it has no solution. So what do? We form instead the next best thing. The next best thing is to find the x such that the norm of ax minus b squared is minimized. So we cast it into a minimization problem. That's what we were doing the last time. And what we found is that this is actually equivalent, interestingly enough, to solving a linear system of this form. ATAX equals ATB. So what happened here, we converted this long thin matrix A, so the A looked like this. It's a tall and thin matrix. We converted it into a square matrix n by n, right? Because AT is n by m, and I hit it with m by n, I get n by n, right? And ATB also is just an n by 1 vector, right? And n is still, and always was, n by 1, so it still is n by 1. And these two problems are equivalent. Importantly, the solution of this problem always exists. If the matrix A has full column rank, that's linearly independent columns, then the solution is unique. So this system has a unique solution. I'll actually close the door. you see it? Any questions?
I just couldn't really read it.
Huh?
No, at first I couldn't really read it, but now I can see it.
Okay. Okay, so what I was saying that if A has full column rank, then ATA is invertible. So I have a unique solution, right? And that the unique solution is then this. ATA inverse, if it's invertible, I can do this and this, right? The key fact in proving this equality was that the null space of A is equivalent to the null space of ATA. Now I'm not gonna go there again because we discussed it the last time, but this is maybe also worth remembering. Now another thing worth remembering is this special matrix, which is sometimes called the pseudo-inverse of A. So what is the dimension of this matrix? You tell me. What is the if A was m by n matrix? What is so the pseudo inversion? So sometimes it's like denoted like with this symbol or with like plus or something. The pseudo inverse, and by definition it's this. Right now we only have it defined when the A has full column rank, but later when we get to SVD we will like extend the definition to like arbitrary matrices. Yeah, then it gets a little bit trickier, but let's just assume for now A has full column rank. So what is the dimension of the pseudo inverse? Sorry? N by m, exactly. So now this interesting thing. What is the interesting thing? It has the same dimension as transpose, right? Transpose also from m by n produces n by m, and so does the pseudo-inverse. So the pseudo-inverse, you can think of it as sort of glorified transposition, and I will comment on that in a second. The one thing I wanted to mention now is, so this AX can be interpreted as the point that get us as close as possible we can to B, right? Yeah? Question? Sorry, I didn't hear you.
Which one of those underlying is the pseudo inverse? The one that's multiplied with.
Oh, this whole thing. So the ATA inverse times A, this entire thing is the pseudo inverse of A.
And the one above it that is multiplied by.
Well, this I meant that this thing is the pseudo inverse, including the T, but not with the B, right?
So the second one there should be that A transpose.
Oh, you are absolutely right. Thank you. Yes. And I would notice this error from what I'm going to say next. What I'm going to say next is, so the intuitive or geometric interpretation of AX is, that is the point that gets us as close as we can to B, right? So if we know that the X can be computed like this, then obviously AX is just this, right? I just put there the A. X again. Yeah, thanks for checking on me. I sometimes can and will make mistakes. Some teachers say that they make it on purpose, so they like make you be on your toes. And this matrix here, this is the pseudo inverse, right? These three guys here, and this is I just multiplied with A, right? And if I look at this thing together, so this thing is a projection matrix. So this matrix P, which is A, ATA inverse AT, is a projection on the column space of A. This is fairly obvious from what we were from the discussion before, right? Because the AX obviously can generate only vectors in the column space of A, right? And this AX thing for the X given as the solution of the least squares problem is that X that gets us as close as possible to B, right? So this is really a projection of B on the column space of A. Yeah, and I wrote a nonsense here. That's why because that there should be no x, right? It should be b. Now it makes more sense. Well, all I wanted to do here was to plug this x and plug it and put it into ax, right? So all I want to do is put a here, which means putting a here, so there of course needs to be b. I'm making a lot of mistakes today. Sorry about that. No, this is actually on purpose to test your attention. So this p is a projection operator. So the p is actually a generalization of our, remember we had a projection on a 1D subspace, on a line passing through the origin. Do you remember how it looked like? If I had a line given by a vector a, how did my 1D operator that we had like 2 classes ago, how did that look like? It was similar to this, right? So it was like lowercase a instead of uppercase a. Do you remember that? You should remind these things for the midterm, like these things can be happening there. So the operator was like this. So if my A is an Rn vector, then this, you should know by now, is n by n matrix because it's AAT. So AAT is the matrix, ATA is the norm of A, so that's just a scalar, matrix divided by scalar. And this was also a projection operator. So maybe I could call this P lowercase a, and this would be P uppercase a. And it's the same idea, except that this was only projection on a 1D subspace, and this was projection on a subspace of higher dimension than 1. So this is a generalization of this. This was only the special case, the simple case, when I have just a 1-dimensional subspace. Now the projection operator has the same property as the 1D one, in the sense that if I take the PA and square it, what I get, take a look at this. ATA inverse, and now AT, and now watch me so I don't make some mistake again. ATA inverse AT. So look at this, I have ATA here and ATA inverse here, right? So that means that this entire term is just identity, right? So that means that the identity disappears, identity does nothing interesting, it just returns me whatever I give it. So this is just this, right? And that's again just PA. So this really has the property that its square is the same as non-square, right? And that for a projection operator that makes sense, because once you have already projected it once, you don't really have to project it again, right? Oh, by the way, there is a common mistake. So yeah, so this mistake I'll actually do in purpose. So watch this. So what if I do this? Because now you might be like thinking that everything reduces to identity, right? So I could do this. A inverse transposition. So inverse transposition means both inverse and transposition. AT, right? But because this is A inverse, that's identity, and because inverse transposition is just inverse of the transposition, is also identity. So this looks like this is just a complicated form of writing identity, right? No. Where did I make a mistake here? It would be sort of stupid if every projection operator was identity, right? Yeah.
Is the transposition of the inverse different from the inverse of the transposition?
That's a very good question, and the answer is no. So if I have, so that's so good question that I actually anticipated it. So the question is basically this, right? If these two things are equal, right? Assuming everything is defined here, right? So if the transposition of inverse is the same thing as inverse of a transposition. And the answer is yes. These two things really are equal. And the way to see it is I can write this. I can do A inverse transpose times A transpose, right? Then we have the rule that we can put the transposes together. So this will be A inverse transposed. But A and inverse is just identity. So this is just transpose identity, which means just I, right? But that means that AT is an inverse to this, right? That's how inverse was defined. In other words, I can write that AT inverse is this, A inverse transpose, right? And that's exactly that. So it doesn't matter if you first transpose and then invert, or first invert and then transpose. It's like beautiful commutative diagram. So this actually is true. So we don't normally bother with like differentiate, because it's the same thing. We don't write this. We just write minus transpose, because it doesn't matter which way you look at it. Yeah.
Is it maybe the order of operations? So when you have A, T, A, -1, and you switch them around when you do the equation on the right, you have them as A, -1, A, inverse T, instead of the other orientation?
No, this is true, right? We know that like if we have inverse, I should have written AB,
Oh, yes, sorry.
B inverse, A inverse, right? It's just like transposition works, right? That's what I have to use. This is true. Right? Now the catch here is, and this is something you should always look for. Maybe there will be like a trick question in the midterm, maybe not. The problem is that this A inverse is not defined, because inverse is only defined for square matrices. But here I sort of fooled you by taking inverse. It looks fine on the paper, right? I know. But A is rectangular matrix, and there's no inverse defined for rectangular matrix. All we have is pseudo-inverse, but pseudo-inverse is not a real inverse. We even have like a different symbol for it, so you don't confuse it, right? So this is nonsense. I cannot, A inverse doesn't exist. Yeah?
Is it possible that A is a square matrix? That could be
If A is a square matrix, then this indeed is possible. And that's the special case, right? If M is exactly N, then what does that mean if M is exactly N?
That means you have the same number of points as dimensions or something?
That's right. So there is, so if it was also, we assumed also linearly independent columns, right? That means there will be always unique solution, right? So in 2D, it's actually good that you brought it up. In 2D, always if I pick 2 points, except for one corner case, I can always put a line through them, right? Uniquely, no problem. Yeah. It's actually super cool to see how the algebra relates to the geometry, right? Yeah.
What's the corner case for the 2 points now?
Well, what do you think what would be the corner case? What would you think would be the corner case? I mean, this is only if I represent my line in this way as I had on the previous example, right? With parameters M and C. The corner case would be if I had the points exactly on the same coordinate, right? Because then M would have to go to infinity. But it's just a problem of this representation, really, right? I could also represent the line as AX plus BY plus some constant C, and that does not have this problem. Anyway, my point was not to like dig deep into this example, but just make you aware that you need to be careful about these calculations and always think what these letters actually mean. So there is another very important thing. So if A happen to have orthonormal columns, so right now this maybe I will like even do it on a different paper so it doesn't confuse you. So assume that A has orthonormal columns. Orthonormal. So it's still rectangular, right? It's still tall and thin, but now I assume it has orthonormal columns. What does it, so this is exactly equivalent to saying that ATA is identity, right? We have been through that when we were discussing orthonormal matrices. Remember that? So these columns, these guys here, are orthonormal, right? If I transpose the matrix and multiply it with A, I'm just doing dot products of orthonormal vectors, which has to give me identity. Should remember this. So what does it mean for least squares? That means if I form the normal equations, this ATAX equals ATB system, Isn't that beautiful? ATA, if A has orthonormal columns, ATA is identity. So I immediately have the solution. I don't have to invert any matrix. That's another reason why orthonormal matrices or matrices with orthonormal columns are so important, because they simplify this problem a lot. Right? Before you would have to worry about computing the inverse of this, and computing the inverse is no easy job. Even if you want to compute the inverse in MATLAB, it's fine for small matrices, but if your matrix has like 1,000 by 1,000 or 10,000 by 10,000 or even more, that's pretty difficult to compute inverse. If the matrix A has orthonormal columns, you don't have to compute any inverse. The inverse is trivial. So that also means that the pseudo-inverse in this case, so pseudo-inverse was this. Let's see if I can get it right this time, right? This in general is the pseudo-inverse of A. But if A had orthonormal columns, then again, this thing is identity, right? So in this case, the pseudo-inverse is exactly transposition. So we have seen before, and I pointed out, isn't that interesting? The pseudo-inverse has the same dimension as transposition. And if A has orthonormal columns, then the pseudo-inverse exactly is transposition. So the pseudo-inverse essentially is what the transposition would be if A did not have orthonormal columns. Or another way you can look at it is this ATA inverse thing is there to compensate for not having orthonormal columns to begin with. And one important thing I would like to point out here, I just had a discussion with a PhD student of mine who was struggling with this fact. It was a little more complicated, but was essentially this problem. What do you think is AAT? That's the right answer. It's nothing. It can be, we don't know much about what it is. It normally is not identity. That's my point. ATA is identity, but that doesn't mean that AAT would be identity. And more likely than not, it will not be. Actually, it will never be identity unless we have a square matrix, and unless M is N. Right? And in the case A is square matrix, then this is true. But in the case that this really has at least one more row than column, then AAT will never be identity. And I think it's true to say never. Yeah, but I will not bother you with reason. Okay, so the point of this exercise was to show that if A had orthonormal columns, then the least squares problem becomes really trivial, right? So the next step is, if we want to solve least squares problems efficiently, maybe we can always turn A into an orthonormal matrix. And this is the idea. So if we have an A which does not have orthonormal columns, we would sort of like to transform it to this version of the problem, which is simple, because, as we say, we don't need any inverse here, right? So we sort of want to transform arbitrary A, which has just linearly independent columns, not necessarily orthonormal. And the way we do that is called a Gram-Schmidt orthonormalization, or a Gram-Schmidt process. It's a very useful thing. Oh, but I just realized I forgot to give you the second example on least squares. Actually, let me do this first, because before we go to Gram-Schmidt, because this is sort of related to what is in the project 4. So let me comment on that first. Okay. Yeah, it went so nicely that I would forget about this example. But so this example was the least squares fit of a line, right? So our model here was a line, so it had two parameters, M and C, and was just a linear multiplication. Oh, it was an affine form of them, so it was mx plus c. This was our model. which we wanted to explain our data with, right? So our data were points, every point has an x coordinate and a y coordinate. We have a bunch of points, in this example 5, but you can have a million points and nothing really changes. Actually, as I mentioned, that there is an interesting thing. If I have a million points, this computation is still very simple, right? If I have a million points, here I get, again, just 2 by 2 matrix. So it's actually pretty cool. That doesn't matter so much how many points we have there. So if I have some points which form a cloud like this, or if I have points that would be looking like this, something like that, probably doesn't make a whole lot of sense trying to fit a line to this, right? So I might be thinking, but maybe there is some other curve I could fit to it, right? And least squares are really universal in the sense that you can fit not just lines, but many other types of curves. This is one example. This is what I wanted to show you, and almost forgot about it. That's part of the, or a version of this is part of the project 4. We'll be solving this week. So let's say we change our model. Let's say that our data, like we measured something like this, and there is some noise, obviously. So there might be even outliers. There might be like some point here and there, and like something went really bad in the measurement, right? What are you gonna do about it? The data are like this. And we can say, okay, line obviously is not gonna cut it because the data don't look like a line even approximately. But let's try to find some, fit it some other curve. For example, this might look like a third-degree polynomial. So let's say, why don't we try fit it a third-degree polynomial, right? And even though we are just talking about linear algebra, and these are linear least squares, I could even put here like linear least squares example. I can still fit a higher order curve, no problem, right? So in this case, the equations, they would look like I1 is C1 x1 cubed plus C2 x1 squared plus C3 x1 plus C4. Then I have y2, right, which would be C1, that's the same, but now I have x2, C4, y3, C1, x3. Are you getting the pattern? While I'm doing the writing exercise, C3, C4. So in other words, the indices, so those are my points, right? So every point here, this would be like x1, y1 point, that would be x2, y2, and so on, right? So again, it's least squares. So in general, I have no hopes for solving a system if there's like a lot of points. I have no hopes of solving the system exactly. That's why I resort to least squares, and I like say that those are like approximate equalities, that they are supposed to be interpreted in least square sense, that I'm not looking for an exact solution, but as close as possible solution. And this this right-hand side here, I can write as a matrix vector multiplication. So this matrix essentially means, so this I can write it out. So this would be x1 cubed, x2 cubed, x3 cubed, and so on. This would be x1 squared, x2 squared, x3 squared. This would be just x1, x2, x3, x4, x5, and so on, right? And those would be just ones. So this is a short way of writing this, where I assume that these bold-face axes are column vectors. So this whole thing is this cube thing, right? So don't get confused by this cube thing there. Now I have 4 degrees of freedom in my model. Now my model is the cubic polynomial, right? And y are again known, right? Those are the data, the values I measured. That's the vector of y I values. And once I have formed the system, that's basically it. I'm almost done, because all I need to do, so this is again a system of the form ax approximately equals, here in this case, y, right? Here A is exactly this matrix. X is my C1, C2, C3, C4, and y is this right hand side, right? So I know everything I need to solve for except for x. I need to solve for x, and I do the same thing. I do ATA, x equals ATY, and solve it. So the point of this exercise is to show that this linear least squares does not mean that you could not have some nonlinearities in the model. This is the important message here. The linearity means linearity with respect to these parameters. Those are the actual unknowns. And with respect to these, the model has to be linear, otherwise we could not use linear least squares. What would be like an example of a nonlinear model? For example, if I did this, right? C1 times C2 plus C3 plus C4. That would be nonlinear, because here I'm multiplying the two, right? Or if I took C1 squared, right? Or C1 cubed, that would be nonlinear. That we could not do with linear least squares. There is also nonlinear least squares, but that's a different story. It's much more complicated usually to solve. But if I have some nonlinearities only in the model, only in the axis, it does not matter at all. Because I know these axes, that's where I measured my points. So I can just compute whatever I want with them, right? I can cube them very easily, and all it changes is the matrix. Right? And it doesn't change the method at all. Does that make sense? If it does, then we can happily move to Gram-Schmidt. So even in this example, this matrix will probably not be orthogonal, right? That would be very lucky. No, it cannot really be. I mean, it could be in very special circumstances, but again, it's probability 0 sort of event. So this will be lucky if it will be linearly independent. So what I wanted to get to was, if we don't have an ortho normal matrix, a matrix with orthonormal columns, if we have just a matrix with linearly independent columns, how can we turn it into a matrix with orthonormal columns? And this is called the Gram-Schmidt process, or Gram-Schmidt orthonormalization. So it's an algorithm, and I like to describe algorithms by describing their input and output. So input in this case is n linearly independent vectors, a1 to an, those are vectors, from R to M. That's input. And output of Gram-Schmidt is orthonormal basis. Or let's say this. Output are vectors q1 to qn from Rm, which are orthonormal. And the span of q1 to qn is the same as the span of a1 an. So in other words, as input you give Gram-Schmidt n linearly independent vectors, and on output it produces you an orthonormal basis for the space, for the linear subspace generated by these n vectors. So that's a pretty cool algorithm, and it's actually also very simple. The idea is very simple, and it's super easy to implement it too. I implemented it several times. There's some numerical funniness here and there, but the implementation, even in C, was like 10 lines or something like that. So the algorithm proceeds in like 2 steps, where the second step is really simple. So I will describe it first for n equal 3. So I have just 3 vectors. They can be an arbitrary dimension. The m can be a million. Doesn't matter. I just picked the 3 because it's just easier to show it with 3 than like always write n and ellipses. So there are 2 steps to this algorithm. The first step, it creates an orthogonal basis. Create orthogonal basis. So B1, B2, B3. Of course, from Rm. So I just simplify my life a little bit and just say that for illustrative purposes, n is 3. But after I explain for n is 3, it will be very clear to you how to do it for 4, 5, 6, or 2 million. So in the first step, Gram-Schmidt produces an orthogonal basis. And of course, once I have an orthogonal basis, then it's very simple to get to orthonormal basis, right? If I give you the orthogonal basis, how do you give me an orthonormal basis back? Yeah, just make them unit length, right? So the second step is just normalize. So I just do this. I just do the result Qi equals Bi divided by norm of Bi. I is 1, 2, 3. So so the second step is absolutely trivial, right? The whole problem is how do I get the orthogonal basis? And the idea is very simple. So now we will be talking just about the step number 1, so I'm given 3 linearly independent vectors. So I'm given A1, A2, and A3 from R to M. It could be R3, it could be R million, doesn't really matter. And I construct the B's, the orthogonal basis, which spans the same subspace as A1, A2, A3. So I start, I do it one by one. That's the idea of Gram-Schmidt. So I start by by defining B1 as, so this means define, or assignment. I like in programming would be like assign to variable B1, variable A1. So the first one, I just take the first A1, and say that's it. Now the interesting thing comes with B2. What is going to be B2? So what I need from B2 is that B2 is orthogonal to B1, right? It has to be an orthogonal basis. So by the way, if I just did the B1, is that an orthogonal basis? Yes, of course, right? One vector always is orthogonal basis, unless it happened to be 0 vector, but that's a weird corner case. So for one vector basis, I'm fine, right? So this B1 is orthogonal basis. And because I assume that the vectors are linearly independent, that the A1 cannot be all zeros. So now what do I do for B2? So for 2 vectors, it's sort of easy to draw an image. So if my A1 looked like this, if I had an A2 that looks like this, so I need to produce B2. So I already said that A1 is the same as B1, right? And I need to produce B2 such that first, the B2 is orthogonal to B1, that's this condition. And second, I can write A2 as a linear combination of B1 and B2. So the main idea, and probably the only idea in the Gram-Schmidt process, is to construct the B2 as A2 minus the component of A2 in the direction of B1. So let me say it again, it's more slower. I take the A2 and I take the component of A2 on the direction B1. There is some component like this. So this decomposes me the vector A2 into these 2 parts, right? This is one part, this is the other part. And this part I discard. So I take A2 minus this part. And this result will be my B2. So what is this part? The orthogonal projection of A2 on a direction B1. That's why I was just recapitulating a little bit before. So what is that? You tell me that. So if I have vector A2 and now I'm projecting on direction B1. So that is B1, B1T divided by B1T, B1, A2, right? So that's this thing here, right? So this thing, the rest is just A2 minus this, right? I take this vector and I subtract its projection on B1. And that will be my second basis vector. So this is a2 minus b1, b1t divided by the norm, b1t, b1, a2. This is my b2. And you can notice, of course, that b2 is orthogonal to b1. Let's see, we should be able to prove it from here, right? So if I do b1t here, let's see. So this would be b1t, so let's see. b1t b2 is b1t a2 minus, and I just need to not mess up the indices, so this would be b1t b1 b1t a2 divided, yeah, it's gonna work. It should work, right? b1t b1. So this is just a scalar, so this is identity, so this is indeed 0. But I think it's better to look at it. So this is like an algebraic proof. I think the geometric one is more instructive, because if I had a vector a2 and I subtracted off the component, I essentially left only the component orthogonal to b1, right? So that of course is orthogonal to b1. That's how I constructed it. And now for b3, guess what I'm gonna do there? I'm gonna do the same idea. And now I'm gonna take the third a3, and I'm going to subtract of the components both in b1 and in b2. So you could like imagine like a 3D image now that it would be like a a3. I don't really want to draw it because it would make a mess, but you can imagine like another vector poking out of the plane here. And I could again subtract of the components in the direction b1 and the direction b2, right? So again, we know what the projection is, right? So this is the component in b1, a3. So now I'm working with a3, and I project off the component in the direction b1 and the component in the direction b2. So this is unrelated. And I'm done. These are my b's, right? And then the last part is just normalizing them. That's easy peasy. So here is a summary slide of Gram-Schmidt. So now we will like, it of course works for n vectors, not just for 3, right? So this is I have n linearly independent vectors, and I'm constructing an orthonormal basis for the span of these vectors. If I had them written as a basis, it would be the column space of this matrix, right? You know this. And the idea of a Gram-Schmidt is to start with A1. Well, here actually I don't normalize it first. The way I described it, the normalization comes second. I mean, you could normalize it straight away. It wouldn't really change anything. It's just like a technical or implementation detail. The key thing in Gram-Schmidt is that then you take the second vector and remove the component parallel to Q1. The Q1 is what you get from the previous step, right? And that's the result. Again, I don't really have to normalize here yet. I can normalize just at the end of the day. Then I take A3 and I remove the components parallel to Q1 and Q2. The Q1 and Q2 is the vectors I computed in the previous steps. It proceeds by steps, and in every step it's looking at the vectors it produced in the previous step. And after I get to an, then my vectors q1 to qn form an orthogonal basis, and I just normalize and I get an orthonormal. Like here it was written just that it was performing the normalization immediately, which is fine. It doesn't really matter when you do it. I just chose to explain it in the way that you do it, like at the end of the day, after we have the orthogonals. All what's complicated here is to get the orthogonal basis, right? From orthogonal to orthonormal, that's very, very simple. Okay, and another way to look at a Gram-Schmidt process is as QR factorization. Because look at this. The way Gram-Schmidt works is that the Q1, or maybe I can do it here. The Q1 is chosen such that A1 is in the span of Q1, right? That's because they are the same. This is trivial. What is not less trivial is that A2 is in the span of Q1 and Q2, right? I will have to go, right? Now let's see if I can do it quickly. A3 is in the span of Q1, Q2, Q3, right? That's how I always so this is how I constructed Q2, this is how I constructed Q3, right? And because the Q's are an orthonormal basis, that means that, okay, I'll have to finish, so I might do this more properly again next time. But let me just finish it now. So that means that I can write the input vectors as a projection because it's as coordinates with respect to the orthonormal basis. And that leads me to QR factorization. Okay, I'll explain this better next time, maybe a little more. It's sort of annoying having just 15 minutes because I could just get started and it's over. All right, thank you for your attention and for all the questions.